now we're going to move on to Pablo. I'll wait. I think we're going to move 5 minutes ago.
Okay, now, can you hear me better? Okay, very simple question. When did the first galaxies appear? This is in fact simple in italics because, well, there is no a simple question. It might involve defining a galaxy. Maybe we haven't done that in 100 years. What is a galaxy? And if we probe the very first galaxies, maybe we have to define that. And in fact, it's one, or for extragalactic astronomers, maybe the main JWST goal. There are two ways to answer this question. One is going to nearby galaxies, and we have done this in the local universe, and look at the fossil record in nearby galaxies. Try to estimate star formation histories and see when galaxies appear in first place. Okay, that's the fossil record going through star formation histories. And the second approach, and I'm going to cover both of them, is going directly and trying to find galaxies at the highest redshift possible, confirming them and study them in the most detail possible. Okay, so I'm going to go to the first approach. This is something that Casey also showed, the typical work of having a spectral energy distribution. In this case, this is a redshift 4 galaxy, and we have data from the optical observed to 5 microns. This is what we have had for 20 years with ground-based telescopes or telescopes such as Spitzer. Okay, and we have fitted star population models and tried to get psi-ion or the star formation history of a galaxy. I'm interested in the second 12 point. But if you notice this spectral energy distribution and this model, we are probing 0.1 nanojanskis. In fact, I'm going to turn that into picojanskis, so you are the first one to see a SED in picojanskis. And if you are as old as me or older, maybe you are more used to magnitudes, this SED is magnitude 34. We are not detecting magnitude 34 galaxies with JWST because this is not a galaxy. This is a real spectral energy distribution, but of this pixel in this redshift 3.7 galaxy. The idea here is that small parts of a big system should be more simple or maybe less complex than the whole system. So if you go to small parts and calculate the star formation history, probably you do a much better job. And if you add all the star formation histories of individual pixels, you can get the star formation history of the whole thing. And here's what I'm doing. Fitting all the pixels as we go, okay, and this is the total star formation history of this galaxy at redshift 3.7. And this is something that JWST allows to do in the same way that we have done this for whole galaxies for 20 years. Now we can do it in a pixel by pixel basis up to redshift of, in this paper that I'm going to show you about, redshift of 7 and even beyond, okay? And with that we think, and we have tested, that we can get a much better, much more reliable star formation history. In other words, this is something also that to get star formation history, sometimes you just go very roughly and put your galaxy in a UVJ diagram. UVJ diagram, if you are a quench galaxy, you are here. If you are an obscure star forming galaxy, you are here. And if you have star formation, carrier star formation, but not very scoop, you are here. And normally you put a point for each galaxy. In this galaxy that I showed you, we can do that with JWST points, 1 point per pixel. And you see that some pixels cover some regions, some pixels cover the other, because there is a complicated star formation history in this galaxy at redshift 4. Okay? And then you can build maps of the star formation rate, of the mass-weighted age, the mass maps, or attenuation maps. This is the example of the galaxy I showed you before. This is another galaxy for which we had this information in the far-infrared about the dusty nature of this galaxy. This is a zoom on the MIPS-24 data. You see the pixels there. This is the same galaxy for The lights do not make justice to the object. This is the same galaxy for JWST, and you can see, no, it's okay. And you can see that there is a knot of dusty star formation surrounded by many other things. And you can do a map, and you can recover. This is the attenuation map, the region where the attenuation is the highest. So we can do a much better job in star population modeling going to a 2D. And this is the main result of the paper that we put together in 2023 with the Sears team, for example, cases in the Sears team and some other people, understanding the star formation history or the tracks in a star formation, specific star formation rate versus redshift or ratio H of the universe plot. This is a very complicated plot, so I'm going to break it for you. Okay, it's more or less the same. So this is the plot. I'm going to break it for you. In this paper, we put together more or less a stellar mass selected sample of galaxies between redshift 3 and 7. And we calculated star formation histories with a 2D approach, much better than you could do before. And then we tried to see when they started to form stars. In this stellar mass selected sample, there were roughly 3 kinds of sources. Sources with very active star formation, many of them some limited galaxies, many of them detected by MIPS, so dusty star-forming galaxies. Some others are not detected in dust emission, probably because our data for that is not good enough for JWST. And this is the average track of these galaxies. These galaxies lie at redshift between 2 point something and 6, okay? And this is the average track in this plot of the specific star formation rate versus age of the universe. And you can see when they started to form stars. This is one of the types that we detect, galaxies that we detect at these redshifts with JWST. This is another type, quiescent galaxies, and we can do the same. And this is another type at this point, at this time in 2023, we call them extreme emission line galaxies. These are in fact little red dots. Okay, we had it in our sample, and this is the star formation, the light and the star formation history of these galaxies. So this is all joined together, and this is the tracks of each individual galaxy. And you can see that these tracks tell us, with the fossil record, that you should have a lot of star formation at very high redshifts. These magenta points over here are the galaxies that confirmed spectroscopic redshift at redshift larger than 10 in 2023. Okay, now we have many more. And you can see that the tracks tell us that the bulk of the galaxy population at redshift between 3 and 7 lies below, in a specific star formation rate, these confirmed galaxies. So we were only probing the very peak of the iceberg of this population at very high redshift. So the idea then is going to the second approach and try to probe the bulk of the star formation of the galaxy population at redshift larger than 10. And even these tracks tell us that there should be significant star formation, significant galaxy formation at redshift beyond 15, up to redshift of 30. So why don't we go there? That's the second approach. And for that, we went to good south. We observed the Hubble ultra-deep field with MIRI for 60 hours during GTO time, and then for 130 hours in GO time. Very deep, 5.6 micron, 7.7 and 10 micron data, 60 hours, 45 and 40 hours exposure in the Hubble ultra-deep field. But in parallel to that, we obtained NIRCam imaging, and we reached 100 hours per band in the relevant filters for NIRCam. So in this region over here, which is called by our survey GTO, MIRI GTO MIDIS, and also by another very big project called NGDEEP, we merged everything together, and we got the deepest NIRCam data available on the sky to probe the very, very early galaxy formation, redshift above 10. Again, this is not good for a projector, but this is all HST data, new Hubble data, new JWST data in the Hubble ultra-deep field. This is not our data. We have even deeper than that, but I had to skip because in the lack of time. And this is the what we had in 2023, trying to probe galaxies up to redshift 13 or so. In green, spectroscopically confirmed galaxies. In black, all previous candidates at these redshifts, and we put together these candidates at redshift 13. But this is the old data that we had in 2023. Now we have the whole data set, NGDEEP plus MIDIS, and we went beyond that, okay? This is the luminosity functions at all redshifts. Here is the new data compared with the old data. This is 277 new data compared to old data, 444, 90 hours exposure time, old data compared to new data, and this is 2 micron. New data, all data. You can see the cuts are exactly the same. The noise is going down like square root of t. I was going to say as crazy, but square root of t. Hopefully it could be better. And this is a comparison of the old data with the new data in an RGB image. Okay, the same that I had told you with beautiful images in a plot. This is the depth of the surveys that we had 1 year ago, reaching magnitude 30 point something, even 30, 31. This is the spectroscopically confirmed galaxies. Now my plot is cut at redshift 11. Remember that we saw a plot cut at redshift 10 in the previous talk. Redshift 11 is my low redshift, okay? I want to probe this galaxy, this regime, okay? These are candidates before we arrived. This is our data, magnitude 31 point something, 0.4.5 in the relevant filters, 2 to 77, 356, and 444. And these are our candidates. We have 6 candidates at redshift 17 and 3 candidates at redshift 25. And this is some star population models. Too complicated, I will skip that. These are the luminosity functions at redshift 17. Redshift 17 is 210 million years after Big Bang. And this is redshift 25. There are a bunch of other estimations, most of them upper limits. For example, this is Castellano. We are probing redshift 25, which is 130 million years after Big Bang. So very, very early star formation. Okay. And the main results in this paper, I don't know how long I have more, but are summarized in 2-3 plots that I have here. First, this is the evolution of the luminosity function above redshift of 10. Every single luminosity function estimation that I have found, okay? First, big result for me is that we agree very well at redshift 10, 11, 12, many different works with different data sets, with different approaches. We agree very well. All of us are right, or all of us are wrong, okay? At redshift 14, things are a bit worse, but redshift 14 is strange because they are not probing these surveys this specific redshift, but at redshift 17, more or less okay, factor of a few point x, okay, and redshift 25 there is only us, okay. What do the models tell us about the evolution of the luminosity function? So these are some state-of-the-art galaxy simulations, galaxy formation models, which are parameterized in something that is called star formation efficiency, the amount of baryons turned into stars at a given time, okay? And, well, they do well with a relatively low star formation efficiency, 10 to 30%. They run high at redshift 10, but you need to go to these values at redshift 11, 12, but they start to be too low at higher and higher redshift. Since that there is an evolution of the star formation efficiency. If we show the models for a higher star formation efficiency, 50 to 60%, they do better at higher redshifts, okay? It's that redshift 25, even if we go to 100, we don't see anything there, but at the other redshifts, 100 is well above the luminosity function, so lambda CDM is not broken according to these models, but we need some evolution of, that's something that that Aaron wrote in his paper, in fact. Okay, this is the same, seen in evolution of the UV luminosity density. I don't want to stop here. I just want to emphasize that, you know, I was involved in the determination of this local estimation of the redshift 0 star formation red density of the universe. We were probing minus 2.5 in log rho, okay? Now we are probing minus 5, okay? I was working with galaxies of magnitude 15 20 years ago. Now I'm working with magnitude 31, so a million times fainter. I have increased the galaxy redshift by, I think, 300 or something like that too, and 20 years. Not bad. Okay, the last two things that I want to say is that in this paper we also did an exercise. What we did is an abundance matching exercise between dark matter mass function and the UV luminosity functions that we have estimated at several redshifts ourselves and some other people. So these are a sketch of what we do. We match the abundance of all those, and then we can get, in order to go from one to the other, we have to account for the dark matter mass to light ratio. We are not very used to dark matter mass to light ratio. we normally work in stellar mass to light radio. To go from one to the other, you have to multiply by the abundance of baryons and by this, which is the emissivity of the stars. The emissivity of the star depends on the age, the metallicity, the IMF, and the star formation efficiency that I have shown you before. Okay? And with that, you can go to the mass to light radios. So this is what we did in this plot. Three things I want to take from this. First, at redshift 25, 17, 12, 11, 9, we are probing halos of different masses. At redshift 25, we are probing 10 to the 8.5 solar mass halos, dark matter halos. This is the dark matter mass. At redshift 17, we go to 9.5, and we go to redshift to 10 to the 11 at redshift of around 10. Second is that here the lines tells you what is the mass to light ratio for different stellar populations with different metallicities, with different IMFs, okay, and with different ages. In gray, we have a very young age, so burst star formation, and this is more 5 minutes? 4. I think I'm fine. So you can see that you can understand the behavior at very high redshift in terms of star formation efficiency, but also if we are seeing stars of very different nature, or with different IMFs, or with different metallicities, everything is entangled, so we don't have, I think, the data yet to disentangle something from the other. In fact, I have put some number here. If you go from POF3 to very low metallicity, 0.004, which is below 10% solar, the FET in mass to light radios is of the order of 40%. The FET in IMF could be up to a factor of 3, and the FET of burstiness could be a factor of 10. So all those four effects have an effect in the galaxy population at these redshifts. So we need more data to disentangle what is going on. This is another characterization of the sample. Typically, the UV slope is around minus 2.6. That's not what some of us expected before. We thought that we were going to see very blue things, but now I think everybody's convinced that the nebular emission in these galaxies is so strong that it affects the UV slopes, and then you don't get very low values. But in our sample, there are a few with very low values, minus 3 or even below. So we are seeing maybe an effect of the IMF or some other quantity that I have. Last results in the paper. In fact, this is not our paper. All that I have told you before, try to understand the nature of these sources based on star formation alone. But some people say that it's very hard for the baryons to coalesce so quickly 120 million years after Big Bang. So they invoke other explanation. For example, in this paper, they saw that the evolution of the UV luminosity density, our points are the orange ones, can be explained by the presence of primordial black holes formed well before any star. Okay, so black holes would preclude star formation. And this is my summary slide. I'm going to go through it because I have time. I think there is a very good agreement between these two approaches that I have told you about, and they are very different. The first one, fossil record in galaxies at high redshift, so you get rid of a lot of time, cosmic time, so that helps. And very different galaxies, quiescent, star forming, dusty, these extreme emission line galaxies, and all of them agree that you should have a lot of star formation in the early universe. And the second approach, that's a 2D approach, okay? And the second approach is going directly to the highest redshift possible. And we have tried to go there at redshift 17 or 25, and we'll have some candidates that hopefully we will be able to try to confirm in the near future. And yeah, we find some candidates. We don't know why the simulation didn't predict these galaxies to be so abundant. And there are several factors that can come into play. I have told you about them. But the question was when did the first galaxies appear? The highest redshift galaxy is 14.44. I emphasize that what I have shown you are candidates at redshift 17 and 25. We are trying to go as high as possible to confirm the galaxies, but even for the redshift 14, 12, 14 galaxies, when you try to get a star formation history of them with a spectroscopy, you see that there should be a lot of stars form a very high redshift, 20, 25. They are consistent in the fossil record in those galaxies. You also see that. So probably we have to go much higher redshift, so we are trying to push the limits. But maybe we are reaching the limits of JWST. Maybe in a spectroscopy already we are there. We have to see. And photometrically, I think we are close, but probably not enough. And I told you that this question about when did the first galaxies appear is also related to the fact that we need to understand what's a galaxy. If a supermassive primordial black hole is there before stars, is that a galaxy? The first cluster is a galaxy, the first globular cluster, so I think we are reaching the same point that we reached with Pluto 20 years ago. Maybe in a few years we will have to define a galaxy. Maybe some things where we will not be able to call them galaxies, and we won't, schools have to learn what is a galaxy and what is not. I will stop there. Thank you.
Thank you again for being on time. So we have time for questions.
As you mentioned, the quiescent galaxy, dusty star-forming galaxy, and little red dots, I was wondering if you think like if it's possible like your highest redshift candidates are some kind of the quiescent galaxy or little red dot, because they also have the same features like the Balmer break, or that's the television that can mimic your Lam break signature, right? So how likely is that it can happen, because your redshift seems to be too compared to other spectral confirmed candidates, right?
I don't know if you're talking about contamination of low redshift galaxies or the actual, of if the galaxies are at redshift 17 and 25, the actual nature. In terms of contamination, of course, we have tried to isolate the most promising candidates. Still, the typical contaminating population is things like little red dots, where you have a red continuum and very strong emission lines. We have tried to use the best templates and the best spectra possible to try to avoid those contaminants, but it is possible. I can tell you that we started from 100,000 galaxies. We arrived to 1,000 galaxies that we inspected by eye, and then the final sample is 9 galaxies. It's not an easy job. It has worked in the past at lower redshifts. According to the spectroscopy we have, that goes down to a certain magnitude, but of course these are candidates. That's a very important point to have in mind.
Thanks.
More questions?
You mentioned the possibility that clusters could provide some of the initial blast of a component of the galaxy. What would be the minimal requirement for the cluster? For example, you could say a million solar masses that blows, forms the stars in, let's say, 10,000 years or 50,000 years. Do you have some rough limits of what type of clusters would be visible at Z25?
If the star formation, if the emission from these galaxies, if they are really at redshift 17 and redshift 25, and we interpret their spectral energy distribution with the stars, the typical stellar mass is 10 to the 7 solar masses, and the typical ages that we are obtaining is 10 to 20 earliest formation at redshift a bit below 30, a bit above 30, 30 to 40, let's say. Sorry? Well, the typical age of the globular cluster, you know better than me, but in the past was 20 gigayears, but
Fabio, did you have a quick question? Hopefully with
Hi,
quick
Pablo.
answer to
Very nice talk. Any of your candidates are redshift higher than like 25? Do you foresee that we're going to get a live spectrum anytime soon, or they are too faint?
We have tried, well, we have submitted a DDT. Jen is here, so she should respond to you better than me. We have also tried with ALMA. I think we are reaching the limits. We think that with heavy, with a few tens of hours with JWST and with heavy binning, we can try to say something. Some of these galaxies are strange in the fact that they are very blue. So maybe there is a strong helium-2 emission. That's something that we expected for the very first galaxies. We don't know. I think we are reaching, the paper is called The Rise of the Galactic Empire. We are reaching the point where the galaxies started to be ubiquitous in the universe and started to rule the universe, at least from our biased perspective. But I think we are reaching the limit of JWST. In terms of spectroscopy, I think we are there. Maybe this is beyond or a bit beyond, I don't know. And photometrically, I think we can repeat more or less what we did in more fields, reaching 100 hours per field per band. I think that's not crazy, and we should go there.
Okay, we need who wants a round of applause again. Switch the microphone. Right. Okay, our next talk is Luigi, who's going to tell us about statistical and physical properties of galaxies in a redshift range 6.